I'm going to demonstrate some of the principles on how lights behave as rays. What I have here is a light source here. You can't really see the features too much because it's too bright for this camera to resolve, but there's a millimeter sign here and there's a couple of arrows going this direction and that direction. So this is my light source, and if I put a screen here, you can see that it diffuses really rapidly, because if I get really close, and hopefully I can get some of this, you can start to see some of the details of that image on the actual screen, but you can see how close I have to be. But light falls off rapidly, the intensity, which we'll talk about later. You can see some of the features here, I can see some of the arrows, but it's definitely spreading out quite a bit into the point where I can't really see it anymore. So, what we can do then is we can put a convex lens in the middle of there. So this is a convex lens, and I can put it in between so that I can get the image to form on the screen by converging those spreading light rays into one spot. So if you see here, I have now, let's give a broader view of this. So I've got this whole arrangement here. I've got the object, this is the source light. The light's traveling through the lens, which is converging all those rays that were spreading out. Remember, they were spreading out here. Now it's converging the ones that are going through the lens, and now I can actually form an image based on some properties of focal length of the lens, which we'll talk about later. And you can see I can see a sharp image there. The thing you can't see is I pointed out the millimeters are on the bottom before. This is actually flipped. And it's also flipped horizontally, because I couldn't really resolve that image down there. It's flipped horizontally, and it's also been magnified over here. But notice if I take this guy right here, and I'm going to move it further away from the light source. This has implications with telescopes. So I'm going to move further away from the telescopes, and look what happens to the image. It gets smaller and smaller and smaller and smaller and smaller. So if you have something, say, at infinity, now instead of magnifying it, now I've actually reduced it. So if you have this object really, really far away, the light source like a star, you end up getting a really, really tiny image, which has implications with how telescopes work. So that's a converging lens, and I want to show you the other example of I've got a spherical mirror here. In a spherical mirror, what will happen here is this light source, the rays will come and it'll bounce off here, and the image will be formed somewhere back here. So it'll bounce off, reflect back here, and the image will be formed back here. And what you'll see here then is if I take this, and this is kind of hard to do one-handed, but let's get this closer. So if I take that close to it and I try to reflect back onto the screen here, I can't quite get it in focus there. You can kind of see it. It's still a little bit too bright. But the point here is, let's move this out a little bit. Sorry if you're getting dizzy at home. The problem is I have to put a screen in the middle, right? So that blocks off part of the light, so I can't get the entire image. But that is the principle of a spherical mirror, is that just as before, it was diffuse coming this way, the lights were spreading out. The spherical mirror takes those and bounces them back and focuses those on a point, and that's what you saw on the screen. So we'll talk about some of the light dynamics and the light ray dynamics of these spherical mirror and the convex lens in the next segment. Object seems to be located at a different position than it really is. For instance, up top, this is the true position of the pen that I'm holding, and in the middle here it looks like it's cut off and it looks like it's coming from a different place. This is because light travels slower as it passes through a medium. This leads us to the ray model of light. We talked about the wave nature of light, we talked about the particle nature of light, and now we're going to talk about the ray model of light, which allows us to trace the path of where the light is coming from. What I have drawn here is sort of a schematic of what you just saw using this glass cube, a schematic of how the light travels as it goes through a slower medium. When it enters at an angle, it'll be, this is, say, vacuum of space, or just the atmosphere, and travels through a piece of glass or plastic. It's going to bend a little bit because it slows down. And then when it hits the other side, it's going to speed up again, and it's going to bend the other way. So what you just kind of observed there was, if I trace this back, this ray looks like it's coming from this direction. So if I have an eyeball here, looking at this, it sees that the ray is coming from that direction, which gives you a misleading result. This is why spear fishermen have trouble learning to originally spearfish. Once they get really good at it, they account for that variable displacement for where the fish actually is. For instance, if the fish was actually here, let's just draw this schematically. If the fish was here, the spear fisherman's standing here, and he's looking into the water. This is actually not in water, I'm just kind of ad-libbing here. He actually sees the fish there and throws his spear here, whereas really the fish was there and he needed to throw it there. Now this isn't exactly right because I'm using a piece of glass, but it was an off-the-cuff sort of example to talk about. So, the thing is, this was a flat piece of glass. This was a flat object. This was a flat object. What we want to talk about is a convex lens, and this is a convex lens where it's shaped. So it'll still bend light in the same manner, but by exploiting this shape, you can get it to focus the light on one point, which is what we just did in the example. You take all that diffuse light, because that light's all spread out, and then you take it and you concentrate it in one area. And this is what a convex lens does. This is a more complicated ray diagram. So a light parallel to the plane of the convex lens, so light that's traveling parallel to this will bend towards the focus point, which I should have drawn on there. It'll bend towards the focus point, and then a light, this is from the same part of the object, light from that position will travel straight through when it goes through the center, and then light on the bottom will travel straight through as it goes through the center. And what you end up having is a virtual image over here that's upside down. So when I was talking about upside down and backwards, so remember this is in 2 dimensions. When we're talking 3 dimensions, it flips and it's reversed, okay? The issue with this isn't really in the telescope nature because we don't have, the object is so far away. Light is so far away that it's essentially at infinity. What we just showed in the example was that the object was actually nearby the lens. But this is a basic understanding that we'll need to understand how refraction telescopes work. One of the things about this is it's dependent on wavelength, how that bends, okay? So that's how a prism works. It's got different wavelengths, and so when it exits this spot over here, it's going to separate into the different colors because these are all traveling at different speeds and bend differently. Actually, this is drawn. They would actually start to bend earlier. Sorry. Look at this. They would actually start to bend a little bit earlier. So if this is white light coming in, it all bends slightly different, and it ends up separating that light, and that's the effect you get from a prism. That's one big disadvantage to refraction telescopes, which we are going to talk about a little bit later. But let's talk about reflection, and then we'll talk about refraction telescopes versus reflection telescopes. Perhaps you've seen this magical effect before, where it looks like I have an infinite amount of reflections in there. Well, that's because the light is reflecting off of this mirror that I'm holding and back to the computer, which is then displaying on the computer. It then reflects back out here, and it goes in an infinite loop like that to infinity, so I get all these various images. What I am holding here is actually a spherical mirror. This is what we just showed in what I showed in the earlier example, and this is similar to what astronomers use. In fact, almost all professional telescopes are built this way, which we'll explain why in a minute, but it is curved. You can see it's not perfectly flat, and this is just actually sort of a makeup mirror. So if you know people, or if you've seen people putting on makeup in these little mirrors, this is what they're using because it magnifies the image, and you can't see this, but I look huge in this image. This is an example of a spherical mirror, which you have seen many of these, and these are very important tools in astronomy. So let me just talk about how the light rays travel off of these different types of mirrors. This is a plane mirror. This is what's in your bathroom. So when you look in the bathroom, you hold up your right hand, and you actually end up seeing it looking like it's on your left, and vice versa. Well, that's because of the way it reflects off of here. So if I trace a light ray here, it's going to bounce directly off the same angle with respect to the center that it hit it at. So you end up getting this sort of perfect, nice geometrical arrangement here. So if this is on the left-hand side, it ends up looking like it's on the right-hand side. If I trace this back, okay? If I trace that, where that light ray came from, I had the direction wrong, and I've got an eyeball here, it looks like it came from back there, and so it looks like, so that original light ray ends up looking like it's behind the mirror. It's not the best explanation in the world. It takes some time, especially with mirrors, to get a handle on this. What I was just showing was the spherical mirror that I had shown on there, and I'm going to show you how the light rays travel there. So, similar to how the convex bends the light rays through the focal point and allows us to focus that light, that's what a spherical mirror will do as well. So, if I have, and let me draw a focal, let's see, through the center of this, and it's called spherical because it would be a giant sphere if you made it three-dimensional all the way around, and that's why it's a spherical mirror. So if I have the focal point out here, actually it'd probably be closer looking at this. If I have the focal point here, and I want to examine how a light ray travels through there, I have a light ray up here, and instead of bouncing off at a direct angle like this, it'll bounce towards the focal length, or the focal point. So it'll go through the focal point, and little arrows will indicate direction, so it's going that way, bounces off the mirror, and then goes this way, okay? So then if I take another light ray, say from down here, and I bounce it off here, and it goes through the focal point. So you can start to see as it gets towards the center here, I'm going to do one right near the center here, it's going to bounce almost directly back. So that in principle is the idea. So if I'm an observer over here, this is why the makeup mirrors, they make everything so much bigger. This is why they're so useful, because you can see much more detail and it magnifies it quite a bit. So if I trace these back, if I trace these light rays back, they're going to end up looking like, where does this one go? This? Okay, they're going to end up making this image look a lot bigger than it normally was. Let's draw a couple more on it down just the bottom, just to give a good idea of this. So here it's going to bounce through the focal point. If I have a light ray coming from down here, here it's going to bounce through the focal point if I have a light ray coming down here. Oops. Is that the right? Yeah, that's the right direction. Okay, so if I trace those back, you can see how quickly this will magnify the image. So if I have an eyeball over here, so somewhere over here I'm observing with my eyes and putting on eyeliner or whatever, and what I end up seeing is a really huge image over here. This was my original image. So this is my eyeball. My eyeball would look that big over here. So that in principle is how spherical mirrors work, and they allow us to concentrate a bunch of light. And I will talk about why there's advantages to using reflecting telescopes over refracting telescopes in just a bit, but first I'm going to talk a little bit about light intensity. Let's talk a little bit about light intensity because it's a very important property when it comes to telescopes. Light spreads out radially from where the source is being emitted. So it spreads like this, although this isn't the most accurate picture. This is just a schematic for understanding. It spreads like this, and as it goes out, it'll get more and more and more spread out. It's a very important factor here. This isn't quite correct with these people drawn on the ground because the star is so far away that it's actually more of a picture like this where they're parallel, which I'll talk about in a second. But this is just a schematic to understand a little bit conceptually of what is going on here. So I have two people standing here. They can see the same star. The star is not just like a laser point or something like that. They can still see the same star because it traces the light ray back there. This guy or this person over here traces the light ray back to there and then sees a star over there. And similarly, all across the Earth or whatever, they're going to see it from different angles. Really, this is so far away that it ends up being parallel to the ground. When it reaches, they end up becoming parallel to each other, and they're not really spreading toward each other. I shouldn't say it's parallel to the ground, parallel to each other. So even though they're spreading here, but this is just a schematic to understand about how light spreads. Okay, so if I took like a little area here, and I wanted to capture all this, say this was some kind of laser point instead of a star or something, and I had this little area there, I could capture all the light. if I come down here with that same amount of area, draw that again, same amount of area. So same amount of area, and you can see I'm missing a lot of the light. So this is how the intensity drops off. So that gives you an idea of how intensity drops off. When we talk about something dropping off like gravitational fields as 1 over r squared, intensity does, electricity does, anything that spreads radially pretty much does. The intensity falls off over the square of the distance. So really far away lights, you can only get a couple of light rays from those actual lights. They're not as densely packed together for really distant objects. So the idea behind a telescope is to gather as much of that light as you can and make it converge to make a clear, sharp image. Okay, so over here, these look like smokestacks, but really they're just like really poorly drawn pseudo-telescopes, if you will, with different diameters, okay? So this one's got a wider diameter, and this one has got a very narrow diameter. What I've kind of trying to draw without measuring this, what I've drawn is light rays. Like I said, they're coming parallel to each other because they're so, for an object so far away like a star or even a planet, you know, anything that's really far away is going to come in parallel like this. That schematic was just to understand sort of the intensity aspect of it. But so what you want to do is you want to build, so this, let's say this is a refracting telescope, and I've got a convex lens in here. I want the biggest convex lens possible to capture as much light ray, because here I got 2 light rays going in, here I've got only 1 light ray going in, so I want to get as much light as possible to get as much information on that star as I can. Okay? So this is the same principle with mirrors, because I want the much light coming into that mirror to reflect back so I can see it all in one spot. So this is the basic principle on why diameter is so important when it comes to telescopes, and one of the main reasons why reflecting telescopes have such a big advantage over refracting telescopes when it comes to manufacturing. So now we've talked about refraction, reflection, and light intensity, and what the purpose is of building bigger diameter lenses or mirrors. Now I think we can talk about how telescopes work. Finally, we get to talk about telescopes, and that's the fun stuff. That is what allowed us to see that Jupiter had moons. It allowed us to see details on the moon, our moon, and now it's allowing us to study the cosmos in ways a lot of the early inventors would have never even imagined. Okay, so first we're going to talk about the refracting telescope. The refracting telescope was the first one ever invented. It was invented by Galileo, who had heard of seafarers inventing a similar device, and he put together a much more compact, reliable telescope using the principles, and this is basically the same type of schematic that a Galilean telescope works on and that you can buy in your backyard to this date, even though it's been over 400 years. A refracting telescope, the idea is the light comes in parallel rays. Before, when I drew the light ray diagram, I had the object that was near, like the lens, and then I had the image over here. Well, the object was close to the focal point, close to the lens. It was a nice situation that way. In this situation, where the light is coming from infinity, the image ends up focusing on the focal point itself. So this would be where the focal length of the lens would be, from here to here. Okay, so this is a convex lens up here. I don't know if I described this yet. We call this the objective lens. This is the most important lens in the arrangement. You can change out these all you want as long as the focal length is the same to get different magnifications. But this is the big lens that you're going to be using. This is the light that the objective lens is the one that gathers the original light from the star. So it takes the original light from the star, and as the convex lens did before, it bends it towards the focal point. So then we have it crossing at this focal point here, which I've touched so many times now that all the rays are missing, and on my fingers. But you take a second lens here, and that has a focal point, a focal length, I should say, where the focal point coincides with the focal point from the objective lens. So then that ends up taking all that light and effectively spreading it again and magnifying the image for nice viewing as I would put my eye there to look through this telescope. Now there are several disadvantages to refracting telescopes. They're still very practical for backyard telescopes, but when you want to make this thing really large, you're going to have this is, you know, a convex lens, and this is nice and tight. But if you're making a huge one, say a couple of meters, it's going to get really thick. It's going to have lots of impurities. It's going to absorb a lot of the light, so a lot of the light won't even pass through, and it's going to be really heavy. So that's one of the big disadvantages, is you want this as big as possible to gather as much light. As I was talking about light intensity before, you want that objective lens as big as possible. So it's nice for backyard telescopes, but for research telescopes, not so much. Another disadvantage is, we'll talk about magnification here in a little bit, but magnification depends on the focal length of the objective lens. The bigger the focal length, the more magnification you get. So in order to get a lot of magnification, you need to make a really, 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 really long tube to be able to exploit the magnification properties. So that is another disadvantage. Another disadvantage, as we were talking about with the prism before, is that it actually is wavelength dependent on how light gets refracted through a medium. So you'll get chromatic aberration. So you've probably looked through some lenses before, some plastic before, and you've noticed that there will be like splitting of the red and the blue lines. You actually kind of see this with the clouds a little bit, but you get chromatic aberration through these lenses. So then you have to have all sorts of tricks with manufacturing and adding different chemicals in there, and that's beyond the scope of me and beyond the scope of what we're going to talk about. But in order to correct that, that's what you have to deal with. So the brighter the object, the more chromatic aberration you're going to get. So that's another big disadvantage in refracting telescopes. But they're still very handy for many purposes, scopes and backyard astronomy and navigation. So let's move on to reflecting telescopes. These are much nicer. The problem is you have to have a wide base, essentially, and you have this big instead of this long tube, you get a wider base type of deal. So the idea here is that this is an opening. This isn't the lens now. This is just an opening. The light comes and it bounces off the mirror, as we discussed in the previous section. It bounces towards the focal point. You put an angled mirror at that focal point, and it will bounce off of that mirror and towards the eyepiece. Okay, so then another light comes in, hits there, bounces towards the eyepiece, other side, and this is actually three-dimensional, so it's coming from all directions, and it all reflects off that mirror and through the eyepiece. Now you lose a little bit of the light in the middle, but it's minimal. It's minimal when you have a small enough mirror and a large enough base. This light that you're missing that gets blocked out here is not that big of a deal as far as that goes. So these are really nice for viewing. You can put your eye there, and it's up, so you don't have to be like under the telescope all awkward. But they're really nice for viewing. But when it comes to professional astronomy, then we're going to be talking about the Cassegrain. One more thing I wanted to talk about with the reflecting telescope is that the impurity, you don't run into the impurity problems that you do with the convex lens in the refracting telescope. You get this perfect light ray bouncing, and that the path of how that light ray bounces is not dependent on the wavelength at all. So all the light will bounce at the exact same path, so you don't get chromatic aberration. So that's another nice nifty thing about a reflecting telescope that gives you an advantage. So what most professional telescopes these days, here in Washington, the biggest one, the biggest public viewing telescope is actually a Cassegrain. That's at the Goldendale Observatory. This is the same principle as this here, as a reflecting telescope, so it's called a Cassegrain reflector because it's still doing the same principle. And the Cassegrain idea is, instead of having this mirror angled, you have it pointing straight down, and you cut a hole in the bottom here, so that the light comes in, bounces off that mirror and back through the hole. Down, bounces off that mirror, back through the hole. Comes here, bounces off that mirror, back through the hole. This is, again, three-dimensional, so that's coming from all angles, okay? And again, this mirror is so small relative to this mirror, in practice, that light you lose is not really that big of a deal. The huge advantage to these is when you can place a CCD camera down there. So I've written that, this could be called the eyepiece. This could be called the CCD, because you could put a CCD camera down there and collect the light, which is actually what most astronomy is these days. This is usually a CCD, or it's a spectrograph, which is a totally different thing. But you can put other attachments down here to collect that light, whereas if it's up here, it's not as easy to fasten those on. Plus, I want to point out, you see the big domes that are around telescopes, and a lot of them, in a lot of cases, are really huge. Like, these are really huge structures. So actually, in that case, this is actually more comfortable for viewing to put an eyepiece down here, because these things can be like 20 meters high, and you don't want to crawl up a ladder to do that, although I have done that actually with a really big reflecting telescope. So these Cassegrains are the most common now, and you can get these in your backyard and everything too. These are really nice for your backyard, because you can take, if you're in astronomy or astrophotography, you can buy a CCD camera mounted on there. The telescopes can track the night sky and collect all that light for several hours to build up a really nice image on the CCD plate. So these are really nice. If I were to buy a telescope, I would want a Cassegrain and a CCD camera. But not really, in Washington, I'm not really sure that that's a reasonable investment right now. So these are the basic principles of the telescopes that are mainly used in practice. So I think what I'll do now is actually show you physically some examples of a refracting telescope and a reflective telescope, because I happen to have one in the back, or happen to have one of each in the back. This is a nice portable refracting telescope right here. This is a Celestron Nexstar. It has a convex lens at the front with a diameter of, if I can get it into focus, 102 millimeters, and the focal length is 660 millimeters. So the focal length then is from here to this point here. That's going to be 660 millimeters for this lens that's right here. So if I look, I've got a convex lens in the beginning. The diameter of this is 102 millimeters across. That's what the diameter means, and its focal length runs along the length of the tube here. So what this will do is it'll focus the light rays down to the end of the tube, where I will come down here, and I would normally have an eyepiece on here, but I don't have an eyepiece. The eyepiece would be where I would put my second lens to actually view through it, and that lens would have a focal point that ends here. This thing right here is just a viewfinder. This helps you spot the stars. This actually gives you a better magnification. This is just a wider field of view, which is the inverse of magnification. So it gives you a wider field of view, and then you can locate your stars a little bit better. So that is a refracting telescope, and it's a rather nice one for backyard astronomy. And let's move on to the reflecting telescope. This is a reflecting telescope. The light enters into here, and so if I put this in there, you can see the mirror at the base of it. This one doesn't tell me what the diameter of that mirror is, unfortunately, but I measured it from the base, and it looked like to be about a 5-inch mirror or so. So that light that you see is reflecting off the back there, and it's coming and reflecting off of this, and hopefully you can kind of see the angle there. I don't know if you can see the angle of that mirror. So this is an angled mirror back here, which reflects it through the tube up here, and this one actually has an eyepiece on it, which actually shouldn't, because it should be put away. And here's where I would actually view the light that's coming through. So if I take this camera and I shine it down the tube, the light's going to actually reflect here if I put my eyeball here, but I can't do that unless I have a second camera. But this actually, although these do actually list some of the things, so this is the viewfinder as was on the reflecting telescope. This gives you a wider field of view than this thing would up here. This gives you a wider field of view so it can help locate stars a little bit. This one actually tells you what the diameter of that lens is, so you can get some sense of how to calculate magnification. One of the interesting things about this is this is kind of an older one, an older model, and I actually find this kind of cool here. You'll see these little gadgets here with these numbers. These are declination. We only talked about altitude, but declination is also important, because star catalogs have altitude have declination and right azimuth listed. So this is how you would control the up or down, and you could lock into stars once you had sort of calibrated the position of this instrument, and you can move up or down, and that's for declination. Over here I have more complex gears, and this is for right ascension, so this kind of moves your thing horizontally back and forth, because right ascension is sort of the equivalent to azimuth for fixed coordinates, and declination is the comparison to altitude for fixed coordinates. So this is kind of a cool little telescope. I wish I had one of these myself. And it's not as awesome as having, say, an 11-inch Celestron, but for all practical purposes, this will give you some pretty cool views. Lastly, I want to talk about telescope location. Where you place your telescope makes a big difference over the type of, or how much light you can gather, and how crisp your image of your view will get. So here I've drawn a couple of different positions here. So this is the top layer of the atmosphere up here, this line. Not a very good drawing, but space is out here. This is the atmosphere here. It's not a definitive line like that, but somewhat similar to that. This is, say, like the top of the atmosphere here. Okay, down here I have the ground, and then in between I have a cloud layer up here. So this is where the clouds kind of form, because you can go above them or below them, depending on what type of clouds they are, where they'll be located. So here is a mountain, and that's just above the cloud line. Okay, so I'm going to talk about these ideas here. So this is from the ground. This is what we did for a very long time. From the ground, you're subject to weather conditions. You have clouds up here. You're subject to a little street light here. So you get street light pollution that affects the type of images you get in your telescope. Furthermore, you've got all this atmosphere to travel through. So if I'm a light ray, and blue is actually a pretty good example, because blue bounces all over the place, blah, 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 blah. I don't get through the cloud there if I'm a light ray. I might get through, it's not always cloudy though, but in general what I want to talk about here is that the gamma rays, UV rays, some of the blue end of the spectrum, they don't really get through the atmosphere down to the ground. Similarly, there's radio waves that don't get through the ground. That's not necessarily important for visible astronomy, but it's very important for other types of astronomy, like infrared astronomy and gamma ray astronomy and X-ray astronomy. These are all important aspects. So you couldn't build a facility on the ground like that to capture that. But a lot of that light gets absorbed by the atmosphere. It's got further to travel through it, so it's going to get reflected, absorbed, and so you don't get as much light when you get down here due to the thickness of the atmosphere. So you've got light pollution, you've got weather conditions can affect when you can view, and you've got a lot of atmosphere to travel through if you're building a telescope on the ground. Here's just a little handheld telescope for this person down here. So if I go up to a top mountain here, above the cloud layer, then I've got shorter atmosphere to go through. I don't have to worry about the clouds here, but the real key is the less atmosphere to go through. And so if I build one up here, I'm in a much better position. Furthermore, the humidity also is dependent. When you see a rainbow, you should kind of have an intuitive sense now. Rainbows act like a little bit of prism. They separate the light, but water refracts light quite a bit and reflects light quite a bit. So you want to be in a really dry, high altitude environment. The drier, the better. The higher the altitude, the better. Because then you can avoid stuff like street lights, clouds, refraction from water in the air, stuff like that. So the perfect locations are high desert mountain locations, which is why a lot of the really expensive and big, huge telescopes are built in the Chilean desert or on the top of Mauna Kea in Hawaii. However, you can circumvent all of this by building a big one in space. So now we're going to make a big telescope. Woo-hoo. So we got a big telescope in space, like Hubble. There's lots of infrared and X-ray telescopes. There's also the James Webb, which is going up soon. And I think I'll talk about a little detail after this little segment. But by building a telescope in space, you don't suffer light pollution. You don't suffer atmospheric conditions like weather. You don't have to suffer through going through an atmospheric layer and all the sorts of distortion. Now I want to talk a second or two while I'm at it about why the stars twinkle. So there's going to be a little turbulence in the air here, and like I said, like water molecules will refract light rays. They're not the only ones. In fact, carbon dioxide reflects. Anyway, reflects infrared radiation, which is why the global warming issues. But the little bit of turbulence in the air will cause the light to flicker a little bit, and then you see it as twinkling stars. It's not the star itself is twinkling; it would be straight light. If you were to be up in space looking at it, it's actually the atmosphere causing that distortion. So what they do is, in adaptive optics, what they'll do is from like this telescope, they'll create a fake star up here by shining a laser light ray, and then they'll calibrate it, and this is really weird. They'll distort the mirrors in real time in reaction to what the measurements they're getting off of the turbulence from the fake star they created, the laser light going up here. So that's what they use for adaptive optics, which are really, really good for correcting a lot of the atmospheric turbulence. But your best bet is still to build a telescope in space.